Welcome to This Explainer. Today, we're going to act as scientific detectives to solve a massive, fundamental mystery of the universe. Honestly, it's a question that sounds super basic at first. Where does stuff actually go when it changes form? But as you'll see, the answer completely reshaped our entire understanding of reality. Let's dive right into this by challenging something you've probably seen 100 times. Picture a campfire. You start the night with this massive, heavy pile of wood, right? But by the next morning, what's left? Just a tiny, feather-light pile of ashes. Just looking at it, your brain immediately tells you that all that matter just vanished into thin air. It genuinely feels like the weight has been destroyed. But hasn't really? Well, to figure this out, we need to test exactly how matter behaves when it undergoes changes. So let's start with part 1, the illusion of change. To get a solid baseline, we're going to look at a physical change first. You know, a change where the matter looks different, but its fundamental identity is still exactly the same. We'll run a really simple test, just like Activity 9.1 from our source material. Imagine we grab a clean, dry beaker and pop it onto a highly sensitive digital scale. We zero it out, pour in about 50 milliliters of water, and then dump in a spatula full of common table salt. We jot down the weight, give the beaker a really good swirl until every last grain of salt dissolves into the water, and then we check the scale again. Now, this is where the hard data gets interesting. Look at the scale reading, 55.010 grams. To our naked eye, that solid salt has completely disappeared. Poof, gone. It's an illusion of change. But the digital scale, it absolutely does not lie. It proves that the mass of the solution is exactly equal to the water plus the salt. It's 55.010 grams before we dissolve it, and literally 55.010 grams after. It's a perfect match. This beautifully illustrates that simple physical changes do not alter mass. Okay, but what happens when the matter actually transforms into something totally new? Let's turn things up a notch in part 2, a bubbly chemical mystery. So we know physical changes keep their mass perfectly intact. Now, let's test a chemical change, where our starting materials react to form entirely new substances, just to see if that rule still holds up. We're going to use 2 classic chemical reactants you probably have sitting in your kitchen pantry right now, vinegar and baking soda. When you mix these 2 together, a chemical reaction kicks off, creating carbon dioxide gas and a few other leftover substances. For our setup here, we pour about 20 milliliters of vinegar into an open conical flask. Then, we take roughly 2 grams of baking soda and just dump it straight in. The second they mix, you get this brisk effervescence, basically a whole lot of aggressive fizzing and bubbling as the reaction rapidly releases gas. Okay, but here is the massive plot twist. We recorded the initial weight of the whole setup, the flask, the vinegar, the baking soda, before they mixed. Then we wait for all that bubbling to calm down, and we check the scale again. The final reading does not match the initial reading. The number actually dropped. We literally have missing mass. Hold on a second. We have to ask ourselves, did the matter just get destroyed? Actually, scratch that. Did we literally erase a tiny piece of the universe out of existence right there in that open flask? Because it sure looks like it, just like that burning wood from earlier. But hey, this is science. We can't just trust our eyes. We need a better experiment. Which brings us to part 3, the golden rule. To figure out where on Earth that mass went, we have to trap our main suspect, which is the escaping gas. We need to tweak our experiment to create a closed system. We use the exact same flask and the exact same amount of vinegar, but this time we load our 2 grams of baking soda inside a medium-sized balloon. We stretch the neck of the balloon tightly over the mouth of the flask and tie it off so it's airtight. Then, we just tip the balloon up so the baking soda falls right down into the vinegar. You get that same brisk effervescence, all those bubbles, but this time absolutely nothing is allowed to escape. And boom, this brilliantly illustrates what was secretly happening the whole time. As the carbon dioxide gas is created, it rushes up and blows up the balloon. And when we glance down at the digital scale, it reads 22.500 grams. If we had noted the exact starting weight of this closed setup, we'd see that the initial reading and the final reading are identical. The scale stays perfectly constant. That missing mass wasn't destroyed at all. It had just pulled a disappearing act into the air in our first test. And that, my friends, is the big reveal. This experiment demonstrates an absolute governing rule of the universe, the law of conservation of mass. It states, simply and beautifully, that matter can neither be created nor destroyed in a chemical reaction. The whole disappearing act? Pure illusion. The atoms simply rearrange themselves into an invisible gas. We actually owe this monumental realization to this guy, Antoine Lavoisier, who is widely known as the father of modern chemistry. He proposed this exact law way back in 1789. He famously laid it out by saying that in every operation, an equal quantity of matter exists both before and after the operation. Let's lock this down in part 4, proving it with math. Now that we've got the theory in our heads, let's cement it by proving Lavoisier's law with some hard numbers and a totally different kind of reaction. Picture 2 flasks. One has a sodium sulfate solution, the other has a barium chloride solution. We weigh them both together right at the start. Then we mix them. When they react, they form this heavy, white solid precipitate of barium sulfate plus some sodium chloride. Now, because this specific reaction doesn't produce any sneaky gases, we can actually just do this in an open system. And guess what? The scale's reading doesn't budge, not by a single digit. Let's map this out in a strict mathematical equation to see it even more clearly. In example 9.1 from our source material, students combined 4.0 grams of calcium carbonate and 2.92 grams of hydrochloric acid inside a closed container. So if you do the math, that's a total starting reactant mass of 6.92 grams. After the reaction finished, they carefully measure the products: 1.76 grams of carbon dioxide gas, 0.72 grams of water, and 4.44 grams of calcium chloride. When you add all those product masses together, you get exactly 6.92 grams. Think about how wild that is. 6.92 grams of matter goes in, and exactly 6.92 grams comes out. The total mass of the reactants absolutely, unconditionally, equals the total mass of the products. Every single atom is accounted for. The law of conservation of mass is perfectly obeyed. So as we wrap up this explainer, I'm going to leave you with one final puzzle to test what we've figured out today. Imagine a student burns 10 grams of liquid ethanol in an open beaker. After the fiery reaction burns out, there is absolutely zero residue left. The beaker is bone dry and totally empty. Does this mean the law of conservation of mass has finally been broken? Or is an open system just playing tricks on our eyes all over again? Think about Lavoisier, think about that expanding balloon, and always remember, in this universe, nothing is truly lost. It just changes its disguise. Thanks for joining me on this investigation.